The materials for the bridge prototype were hand-cut, resulting in rough dimensions. These materials were all cut at once and assembled after. Looking forward, there are a few things that need to be fixed. The deck boards will be cut to the same size as the joists, but will span the length of each section. Before scaling, the 2x8 by 109 joists will be placed 24 inches apart. For the scaled bridge to be 9 inches wide for the vehicle, 2 joists will be placed. This requires 3 rows of 2x8 by 61 beams.
For every beam intersection, a box with an inside scale dimension of 1/4 inch by 1/4 inch will be built, centered and glued on the beam intersection. A rough prototype was installed on the bridge shown here. During test day, a template shown here will be placed for the scaled 1/4 inch by 1/4 inch piling. After the pilings are placed and the template is removed, the bridge deck will be set with glue on the pilings.
Extensive online research was done in order to form a cohesive, reasonable idea of what our hexapedal vehicle should look like and how it should function. We chose to have 3 hinges and therefore 3 servos per leg in order to achieve a maximum range of motion. The torque that each servo would experience was also calculated in order to ensure feasibility of the leg design. Additionally, we chose to have 6 legs rather than 4 or 8 to optimize the trade-off between the center of balance and the power that would be required.
Before we could start designing the legs, we wanted to make sure programming of the leg motion would be obtainable. A feasibility demonstration was built out of cardboard as shown. This also allowed me to start programming and give the mechanical engineers time to design the parts.
While designing the body, we had to consider the given size constraints for the vehicle passing through the tunnel. Once past the tunnel, the vehicle can widen its legs and grow outside the dimensions. Since the vehicle will be able to move side to side as well as forward and backward, it has been designed to go forward over the bridge, not rotate and move sideways across the other section of the bridge. After the one leg was printed, there were some necessary design tweaks for items such as better wire management, tolerance changes for the servos, horns, wires, and screw holes, and redesigns for some parts for increased range of motion.
As the mechanical engineers were designing parts for the vehicle, I was obtaining the correct electronic components. Due to using 18 servos, the max current draw of the system was much higher than initially expected. We wanted to design for max current load on each servo. This required obtaining a 3-cell LiPo battery and using 7 parallel voltage regulators. This system will be able to maintain power for approximately 20 minutes with all the servos at maximum current draw. A breadboard test with all 18 servos was performed. The servos were all fed one control line and the bench power supply provided the needed current. Once the legs were designed and one leg was printed, I started programming movement of the legs. I also established Bluetooth connectivity between the microcontroller and a DualShock 4 controller to allow for user input.